Thanks a lot for having me. Yeah, I want to talk a little bit about open large language models. A lot of people know about ChatGPT. Open language models are a little bit less known, but nevertheless, I think they're here to stay and they play an important role in the ecosystem. I want to talk a little bit in two parts about open LLMs. First, I want to give a little bit more an overview of where we are, what different kinds of companies are doing, and then I want to dive into a little bit more practically what it takes to train a large language model openly with a few projects that we've worked on at Hugging Face. So when we looked at when ChatGPT was released, I told this, I think in the past few days, a few times, people were a little bit like, it's game over, OpenAI is dominating that space. Nobody's even close to training such language models. Nobody even has the money to do it. It's like a multi-million dollar investment if you want to train any language model at this point. But the tide has turned a little bit. So if you look at the newspaper in the past few months, you see like a lot of companies are heavily investing in training models and doing so openly. Maybe the most dominant one is Meta at the moment. They committed to buying 500,000 GPUs by the end of this year. To give a little bit of context, like to train GPT-4 took like 25,000 GPUs for a few months. So Meta is in a good spot to train a lot of GPT-4s very soon. And they have done so with their Llama models, for example. There are also startups like Mistral that are investing a lot. They got a lot of funding and they're investing a lot in training open models as well. And even Google, who's like for a while has been more closed, now opens up a little bit more. And recently they released the Gemma models, which are kind of like small Gemini models in the open. So it seems like the open models are coming back. I say like second spring of open models because one thing that's quite interesting is like the whole revolution of transformers was fueled by open models. At the very beginning, all the models were open. There was BERT and GPT that OpenAI and Google released, and they sparked all the innovation that led to ChatGPT. So it was a bit sad when they started closing up. And I think having open models is like a very big part in innovation. The question is like, can now only companies train these models? And I think the answer is no. If you look a little bit, this is just the landscape of Europe. If you look at the different supercomputers that are public supercomputers, there's a handful of them that are at the scale to train GPT-4 or bigger models. There's Lumi in Finland with AMD GPUs. There's Jules and soon Jupiter in Germany with a lot of GPUs as well. Leonardo in Italy. It's not Leandro, sadly. It's not my cluster. And in Switzerland, there's Alps, which is probably one of the best clusters that's coming online in the next few months. And it has like 10,000 GPUs to train such models. So we don't need to put all our trust in these few companies like Meta or Google. Maybe they decide next year to close down again. There's also compute in the open available to train models. And to show a little bit like how that game over situation that we had when ChatGPT came out changed is when you look at some benchmarks. This is like the LMSys chatbot arena where language models play against each other, and you kind of get an ELO score of which model is best. And you can see the purple line is like the closed models, and they had a very big gap at the beginning. And you see the green line is the trend of the open models, and they're catching up quite quickly. So I think we're soon going to be in a spot where we have a lot of like very good open source models as well.
That's it. Sounds good.
So before I go into the practical details, I want to like clarify a little bit like what closed and open models are and what fully open models are, because there is a little bit ambiguity in those terms. So I think the clearest one are the closed models. These are the most famous one, maybe from OpenAI, like GPT-4, ChatGPT, Gemini from Google, or Claude from Anthropic. You can only access them via an API. You can't run them locally. You don't have any understanding of how they work internally. In the early days, you maybe knew the architecture, broadly speaking, but for the latest models, they don't even publish any information about that anymore. And you can sometimes fine-tune them, sometimes not, depends a little bit on what the company offers. So you're a little bit limited with what you can do with them. Then there are the models that I will call like the open model weights or open weights models. And those are models that you can download. Those companies share the weights. There's Llama from Meta, which is maybe the most well-known model. There's models from Mistral, and there's also very good models now coming from Asia. For example, DeepSeek is a company that builds very good language models. And they share the weights, so the end product of training, but you don't get any access to the training code, you don't get any access to the training data, and that also has puts limitations on these models. So for example, you don't know if your data was used to train these models. You can't remove your data from future trainings. You can't inspect the data sets, what kind of biases they had. One of the most important steps of building a data set for training models is filtering, but depending on how you filter, you introduce new biases into the data sets, and you don't know how that was done. There's also issues more on the scientific side with benchmark contamination. Most of the benchmarks are on the internet, and those models are trained on the internet, on internet data. So you need to be very careful to remove those benchmarks. But I mean, usually they promise they did it, but you never really know. And for scientific reproducibility, it's also a nightmare. So there's the third category, I would say, the fully open models. And those are models that are, you get access to the training code, you get access to the data set, to the pre-processing pipeline, and finally also to the model weights. There's a reason why people are a little hesitant to do a fully open release. For some companies, like giving away what they did on the pre-trained data is kind of their secret sauce. So it's like they're giving away their competitive edge. It's also easier to get sued when people can look at what data went in there. If it's a black box, it's a little bit harder to get sued. So liability issues is a big reason why some of the companies don't want to talk about the data. And whenever you release something open source, you need to maintain it. And most researchers don't want to put themselves under the maintenance burden. So the projects I'm going to talk about are the first one, Bloom. That's a model that we trained 2-3 years ago, and StarCoder, which is a model that I was quite involved in. In the middle, we also have Olmo. It's a model from LNAI, which is also fully open. So the two projects I'm going to talk about is Big Science and then a little bit Big Code. We weren't very creative with the naming of these things. Big Code is kind of the spiritual successor of Big Science. But first, let me tell you a little bit about Big Science. So Big Science happened at the time when GPT-3 was released, and really all the big labs were closing down, so nobody was releasing any models anymore. And at Hugging Face, we thought it would be really great if there would be a GPT-3 alternative. For those who don't know, GPT-3 is kind of like the model just before ChatGPT. ChatGPT is kind of like GPT 3.5. And so we wanted to build an all open alternative. And the inspiration, Tom, who was the brain father of that project, was he's a physicist. I'm also a physicist. We were thinking about big science projects in physics, and CERN is a natural one, right? It's a very big open collaboration where you build something very expensive, but it's open and researchers can contribute to this project. So the question was, can we do something similar? And we did. In the end, I think there were over 1,000 collaborators working together to build a large language models. They were organized in working groups, and there were over 30 working groups with 60 chairs, people focusing on different aspects of the pre-training. And as with any language modeling project, one of the biggest focus was put on data sets. And we have 59 languages in the data set in Big Science. A lot of people, one of the first questions usually is why 59 languages and why is German not one of them, for example? The answer is very simple. For each language that we wanted to put in the model, we wanted to have at least one native speaker helping with the data filtering, because it's very hard to filter language data if you don't understand the language. So if there was nobody willing to do the work in German, there was no German in the final data set. And yeah, in the end, the result of that was like a data set with 350 billion tokens. Token, as we heard from Josh this morning, is kind of like a word, 1.5 terabyte of text. To put that in perspective, Wikipedia is maybe 5 to 10 billion tokens, so it's like much bigger than Wikipedia. We're way beyond that scale now. We needed some infrastructure to train such a model. It's a quite expensive endeavor, and we got a research grant on Jean-Zé, which is a French supercomputer, and we trained a 176 billion parameter model on roughly 400 GPUs on that supercomputer, which was also nice. Like, we built an open model on open infrastructure or public infrastructure rather than on some closed cloud, for example. And one thing that I wanted to show a little bit, because I promised to in the talk abstract to talk a little bit like what it takes to actually scale such a model, is like, how do you distribute one model across 400 GPUs? And we have a model with 170 billion parameters, so that one model doesn't fit on a single GPU. So what do you do? It's like, do you need to build a bigger GPU to go training? And the answer is no, you can parallelize things. There are essentially 3 parallelization methods that you can apply in parallel. That's why it's sometimes called 3D parallelism. The simplest one is you can parallelize the data. So you have different instances of your model in parallel on different GPUs, and they're kind of doing all the same things. They do the training, they get an input and get a loss, and then they backpropagate. But what's different for each instance is the data set they get. So each data parallel instance gets a different batch of data. You then have to do some synchronization where at the end you synchronize the gradients. But that's like conceptually, I would say, the simplest thing you can do. You just parallelize your model as a whole. But as I said, 170 billion parameters don't fit on a single GPU. So how do you get one instance even? And there are essentially 2 ways you can parallelize. There's pipeline parallelism and there's tensor parallelism. Pipeline parallelism means usually these models have a lot of layers. And so you distribute them layer-wise. So maybe layer 1 is in GPU 1, layer 2 is in GPU 2, and so on. And then these GPUs have to communicate the outputs to each other. So that's called pipeline parallelism, because you kind of build a pipeline. The second thing you can do is called tensor parallelism. And tensor parallelism is, rather than slicing across the layers, you slice across a single layer. So you have this matrix multiplication that we saw this morning with Josh, but once these matrices get too big, the multiplication is also quite expensive. So you can break up the matrix multiplication across several GPUs, and that's called tensor parallelism. And you can see here, it's like, in the end, one model instance is the thing on the right, where you have 48 GPUs for one model instance, and then on the left you see, 8 instances of that model. And it's a combination of all 3 parallelization methods. So after big science was around the time when Copilot came out. And so naturally we thought it would be really great if there would be an open source alternative to Copilot. And there was also a lot of criticism around Copilot because it was built on code from GitHub. OpenAI and Microsoft trade code from GitHub and trained a model, and then they monetized it. And a lot of developers felt like that's not really nice. You take all our code and you make money out of it. So we thought, can we kind of build it in the open and give it back to developers? So we applied the same principle. We wanted to build it fully open. We wanted to do it in kind of like collaborative way. And this time we teamed up with ServiceNow, which is like a large company in the US. That has a very large research team as well. And with the research team, we kind of did it together. And again, the first thing we needed to do is like, we need actually a very big data set of code. And there was none out there. So we had to build one. And the way we did it is, this is roughly the pipeline of how we built the first iteration of the data set. You go to GitHub Archive, which is an archival platform that has like information about all the repositories that are on GitHub. And we use that to just get a list of repositories. And with that, we got like 200 million repositories names. And then what we did is like for 3 months, we did Git clones. So we did it like in a massively parallel way, but it's quite expensive and ran on a cluster for 3 months to get all these repositories. Some of them were not available anymore. Maybe they were deleted or made private since. So we ended up with like 140 million repositories or 100 terabyte of data. The first thing we did was we removed a few extensions. We didn't want to train on binary data, for example. We didn't want to train on data, so we didn't want to train on CSV files, for example. So we removed those. That already removed a part of the volume of the data we had. So we were at 70 terabytes then. Then we did license filtering. The nice thing compared to like web data on GitHub is like has a fairly clear license structure usually. So we can look at like what licenses people put on their repositories. And so we did some license filtering. Turns out there are roughly 3 licenses on GitHub. There's Apache, MIT, and no license. And then you have like 5% of everything else. But we filtered for permissive licenses and ended up with 6 terabyte of data. We did some further deduplication, and we ended up with like 3 terabytes of data. Both of these data sets are publicly available, and people can use them. We went a little bit further later on in the project to build an even larger data set because we were hitting a limit. It's a very large data set, but if we wanted to keep up with the closed models, we needed more data. So we built the stack version 2. It's a little bit more open when it comes to licenses, so we also consider repositories that have no license at all as data that we train on. We still don't train on non-permissive license code. But we needed to make some compromise at some point. I mean, during these open projects, you always need to make some kind of compromise. In the end, you want to build a model that's competitive with the closed models. If you don't, then nobody's going to use your model, no matter how ethically or reproducible it is. So we decided to include no license data. I'm going to talk a little bit about data governance that we put on top even there. But as you can see, the data set's roughly 10 times the size of version 1. And we include also more languages. We went from 80 to 600 languages. And if you're a model trainer, you don't talk in terabytes, you talk in tokens. So we have, in the first version, we had 200 billion tokens, and now we have like almost 1 trillion tokens. So as I said, like we were a little bit more inclusive with the licenses, but we still have some data governance tools that we use. One of them is data inspection opt-out. So what you can do, you can actually right now, you could go to an app that's called Am I in the Stack, and you can check with your username which repositories were included in the data set. And if you don't like what we are doing with your data, you can opt out. So the way the opt-out works is you simply open a GitHub issue. That's quite convenient for us because then we can immediately verify you're opting out of your repository because we can check if the username that posted an issue is actually the user, is the same as the repositories you're opting out of. And we also have other tools, like we have a search tool, you can search the whole data set, and we have a membership test. So that's a cool thing where if you use a model to generate some code, within a millisecond or so, we can tell you whether that exact code it produced was in the pre-training data. It's only a membership test, so it's only binary. We can only say yes, no. You still have to use the search index if you want to know where precisely it was. But it can be useful as a first flag because you can kind of use it during programming. You see like a small flag popping up. Yeah, and those are the models that we trained in the chorus of Big Code, and you can see how the cost and the model sizes like evolved. Like we started in October or September 2022, and we had a first model called Sandecoder, came out around Christmas. That was trained on 250 billion tokens. The model had 1 billion parameters and was trained only on 3 languages, only Python, Java, and JavaScript. And to train that model cost only like $8,000. So that's like something maybe a company can afford to do if they want to. But it wasn't the state-of-the-art model yet. That was more like an intermediate model that we trained just to verify our data set is good enough. So we scaled that whole process up The model architecture, everything is pretty similar, but we trained it on more languages. So we went for 80 languages, 1 trillion tokens, and 50 billion parameters. So it's 15 times bigger than SantaCoder. And that was StarCoder 1, at the time the state-of-the-art code model. The language modeling landscape is very shortly lived. It was the state-of-the-art for a few months, but then other models came, and it's not anymore. So we had to scale up our effort, and that's when we switched to the new stack version. That's when we noticed, like, if we want to keep up with everybody else, we need to train for longer, essentially. And that's StarCoder 2. It's essentially the same as StarCoder 1, but trained on more data. So we went from 1 trillion tokens to 4 trillion tokens, and we added also more languages. So we trained now in 600 programming languages. I'm not a computer scientist myself, so I was very surprised that there even are 600 programming languages. But there are some very exotic ones too. Yeah, so we trained models, but a recurring theme, I think, during some of the talks today and some of the sessions is always like, how do you then evaluate and know that your model is actually a good model? And with code, you're in a kind of nice spot because software developers automated testing to some degree, and we can apply the same principles for testing code LLMs. So some benchmarks work in the following way. You have kind of a file with an import and a function header and a doc string, and the task of the model is to produce the function body. In that case, it needs to filter some strings in a list of strings, given they have a certain substring in them. So the model generates a body, and then comes in the nice thing about software development. People have unit tests, so we can actually test if the function is doing what it's supposed to do, and it gives us a nice value. And this works very well for that kind of testing. So when you have a function, which is kind of like a subset of what software engineers do, there are other approaches how you can test like different parts of the model. So I talked about completion, that's one thing, but there are other benchmarks more about code reasoning, which is a kind of a cool benchmark where you have a function and you have an input to the function, and the model needs to predict what the function will produce given that input, which means it kind of needs to simulate what a function does, or it needs to understand what the function does to produce the correct output. There's also a data science benchmark, which tests a few libraries like matplotlib or pandas or TensorFlow, things like that. We can test math reasoning. And we also can test repository context, which is a nice thing. So the model gets information from all your repository and needs to make a specific completion. One of the things building an open model that I'm most excited about is that it builds an ecosystem around the things you're doing. So I talked about the stack, which is the data set that we built. And what we've seen is like every code model that has been trained since we released the stack has been trained on the stack. There's like stable code from Stability, there's CodeGen from Salesforce, there's a model from Replit or Decicoder. There are even most of the closed models we're aware of, they're also trained on the stack, but since they don't talk about what data set they use, it's not publicly known, but they also used it. So that's kind of cool. You put in the work, you build a nice data set, you try to apply some ethical principles. Maybe they're not perfect yet, but you do a first step. And kind of the whole community builds on top of that. The same goes for the model. Personally, I think the most valuable thing we do is the data set, but also the model leads to like a lot of people like fine-tuning it for a specific thing. So there was a company that used StarCoder early on to do SQL prediction. So you get like a query, I wanna find this in my database, write me an SQL query to do this. And they fine-tuned StarCoder specifically for that purpose. And that model beat like ChatGPT while being like much, much smaller and much cheaper to do so. So I think those are the cool things about like building things in the open. You empower a lot of people in the community and on various aspects of the things they're doing.